Well, hi there. Glad to be with you again. And we're just going to conclude our journey with normal distributions in this session by having a look at a few problems. I've chosen three very different kind of problems for you, and hopefully you'll get something out of them. They're really good ones, so let's look forward to that and let's get going. Okay, solving problems with normal distributions. Well, that's the name of the game, guys. So our first problem, let me see, here it is. Well, we've got the limits of acceptability composed on the lengths of a certain batch of metal rods are 1.925 centimetres and 2.075 centimetres. Okay, that's the limits of acceptability, all right? It is observed that on average 5% are rejected as undersized and 5% are rejected as oversized. Assuming that the lengths are normally distributed, find the mean and the standard deviation of the distribution. Well, let's have another look at this question, this knotty question. It seems that the limits of acceptability on the low side would be 1.925, and that must be they must be anything less than that. It's probably less than the 5% that are rejected as undersized. And for anything more than 2.075, that must fall into the 5% oversized bracket, I'd say. Would you agree with me? I think. See, they're not telling us the mean or the standard deviation. We've got to find that, okay? So this is a classic case, guys. We've got to find mu and sigma given known variable values and probabilities, and it is a case for Z. Da-da-da-da! There he is in all his glory and finery. Mr. Z to the rescue. We're going to go back to home base with Mr. Z, okay? Good show. Now, what have I got for you here? I'm showing you a little picture. I love a picture. This shows me a little graphic of the kind of situation we're dealing with there. I've showed you the oversized population, which is 5%, and that's above the 2.075, and I've showed you the 5% under the 1.925. But we don't know mu and we don't know sigma. But don't worry, thanks to Mr. Z, we soon will. So, let's redraw it as a standard normal curve, okay? In that case, we've got mu is 0 and sigma is 1, and if we could just find out those Z values which correspond to those 5% tails there, I think we'd be in business. I do. Indeed I do. Okay? So I'll call them Z1 and Z2, shall we? Now, just that's where we got to, wasn't it? Alright, now I'll show you how easy it is. This is a classic case for Z, where you're just looking at the one distribution rejigged to be a standard normal, and you can work out mu and sigma, as long as they give you enough information about the actual parameters in the distribution, which they have in this case. Yes, there's Mr. Z. So we need Z1 and Z2, okay? Right. Now, we are given, what are we going to do on the calculator? I'm trying to prompt you here. We're given the probabilities. We're trying to get back to the variables. So which is it? Is it normal CDF or is it inverse normal? Come on, get your thinking cap on. Yes, yes. Of course, it's inverse normal, okay? Because we're going backwards. Now, what I've done there is I've plugged it into my trusty calculator, and I've plugged in the values there for the area. In this case, I'm going for 0.95, and I'm going for mu of 0 and sigma of 1. That's the standard normal situation. And what do I get? 1.4, no, what is it? 1.64485. Okay, that's what I get. Now that is the Z value for the equivalent of the 2.075 thingy, okay? 2.075 length, I mean. Goodness me, I'm getting a bit, my language is deteriorating, isn't it? So I've just written it in there, up there for you, okay? How do you like my new pointer? Isn't it a beauty? It's a hand. So therefore, there you get there, 1.6 0.449. Okay, that's the Z value. We found it on our calculator. Now we're going to do the same thing for the lower level, and that's 0.05. Okay, that's the lower tail, the left-hand tail of that distribution. So we're putting in 0.05 and the same mu and the same sigma, and what do we get? We get minus 1.64485. Well, of course we do, okay? That's there. See? Minus 1.64485, and that is the Z corresponding to this here, this value here, okay, which is at the right-hand end of that tail, okay? Now, good, good, and good. I'm writing it in, and I've just written it in up there for you, okay? Now, you watch what happens now, guys. This is really, really nice, okay? I'm going to have two very nice little simultaneous equations. So I'm saying Z1, which was the upper one for the right-hand tail, that's this one here. Where am I? There, okay? That's this one, okay? And that equals, of course it equals, x minus mu over sigma, doesn't it? Well, the x value was, what was the x value? Come on, what was it? Yes, it was here, okay? 2.075, right? There it goes, yeah? And let's just rewrite that out all properly for us. Yes, and I'm going to call that equation 1, right? Now we're going to do the same thing for Z2, which was this value of Z here, which corresponds to this value over here on the actual distribution, doesn't it? The 1.925. So we just put that into an equation. Same thing as we did on the line above, and what do we get? We get that, and that's equation 2. Now, look, how many variables have we got to solve for? Mu and sigma is 2. How many equations have we got? 2. Well, I think we're in business now. We can certainly solve for mu and sigma. So if we add equation 1 and 2, which I've decided to do, then the left-hand side comes to exactly 0 because those Z values cancel each other out. You get that funny looking thing. If you multiply both sides now by a sigma, then the sigma will go away, which is very nice, and we get that amazing looking simple equation, don't we? And therefore, what is mu? I think you could have guessed that, really, because those two values, those 2.075 and 1.925 are exactly 0.075 either side of 2. So there it is. Now, all you've got to do is substitute that value of mu into one of those equations. I've solved it into 1 or 2, doesn't matter. And you can solve it for sigma is 0.0456, Mr. Box. Thank you, Mr. Box. Now, how did you like that? You see that standardization is very, very handy. If they give you information about even one distribution with a couple of reference points, you can work it out with two equations to solve for mu and sigma. Okay, so that's the second application of Z that I foreshadowed in a previous video that I said I'd do later on. Well, now is the later on. I've just done it for you. Okay. Good show. Now, this is the second problem. Now, look, guys, you really should try this problem for yourself before you look at any more on this video, because it's a really good problem, and I don't want to spoil the fun. You can come back and look at it when you've had a shot at it. And the next one is similar. The next one is an absolute doozy. Okay? Right, this one is a semi-doozy. The next one is an absolute mega doozy. Okay? So what have we got? Are you going to pause it, or what do you want to do? All right, you've just made your decision. If you're listening to this, you've decided to keep going, or you've done the problem, and if otherwise you will have paused it and you're busily trying the problem. Okay, the volume of soft drink in a 1 litre bottle is normally distributed. The soft drink company needs to calibrate its filling machine. They don't want to put too much soft drink into each bottle as it adds to their expense. However, they know that they will be fined if more than 2% of bottles are more than 2 millilitres under volume. There's some big hints there for you. Okay, volume being 1,000 mils, I'd say, because it's a 1 litre bottle. Okay, the standard deviation of the volume dispensed by the filling machine is 2.5 millilitres. So they're telling us the standard deviation. What should they choose as the target volume? That is the mean of the distribution. Give your answer to the nearest milliliter. Well, they've given us sigma, they're asking us for mu. So I would say they only need to give us one reference point in that distribution, which they have given us, right? Because we only need one equation. So to solve for one variable. So they told us that they're going to get, they can't go below 2% under volume, below 998, which has got to correspond to 2% of the distribution. Is that right? I think that's right. Let's just start setting this out and see whether we're on the right bandwagon here. Okay, we need to find mu, don't we? Now we're given a known probability and variable value and sigma. So, alright, so what should we do? A case for Mr. Z. Da-da-da-da. Isn't he magnificent? Hello, Mr. Z. You're quite something. So here we go. Let's have a look at this. Let's draw a picture now. Yeah, that's what it is. The 2% tail there has got to be the bit under the 998, okay? So that's the maximum allowable probability we're allowed to have. It said here they get fined if there's more, didn't they? Yeah, more than 2%. So we're only allowed up to 2% at the 998 cutoff level, okay? If that area be left to the left of 998 is more than 2%, we're in big trouble. So that's what we're doing. Yes? Good. Now we're going to Z that. We're going to Z it. Okay? That's the standard normal now. Okay, we've got sigma is 0 and no, I mean mu is 0. Sigma is 1. Yes? Okay. That's the situation. And we've got, if we can find the Z value for that 2% left-hand tail, which won't be any problem at all, I say we can solve that. Okay? Let's do it. That's where we got to. Okay, let's go. What we're saying is we need Z for 2%. So we've got the probability, haven't we? And we need the variable. So what is that? Is it CDF or inverse normal? It's inverse normal. Of course it is. So the area we're looking for is 0.02 for 2%. And we've got mu is 0 and sigma is 1. Yeah, that's right. So what's our Z value? There it is, the RSUB, guys. So can you read that? Minus 2.05375, okay? That is our Z. Da-da-da-da. That's the one we're going to use, and that's our ticket to finding mu, okay? Let's go for it. Therefore, x minus mu over sigma is our Z value, which is minus 2.05375. Don't round that off on the calculator because you don't have to, and you don't want to lose any accuracy, okay? Plug in the values now. 998 is the value of x, mu we don't know, and sigma we're told is 2.5. You see, we've only got one unknown now. It's just child's play from now on. So, there we go. I've multiplied by 2.5 both sides, and I've got that. Now all I've got to do is just do a bit of fiddling, and we've got mu for me and you. There it goes. And it looks to me like 2003, doesn't it? Oh, well, not 2003, 1003.13438. That's right. So that has got to be our target volume. Ladies and gentlemen, to the nearest mill would be 1003. Okay, Mr. Box. So, okay. Now see, the problem that you might be having with those kind of questions is that they're worded long questions and you just can't get yourself stuck out of all the mire of the words into the simplicity of the maths. Well, look, the more you do, the better you're going to get. That's all I can say. You just need practice. Okay? Here comes the mega doozy. We've got a certain amount of chemical in a type A cell. I presume they're talking about a battery, aren't they? Or something. Is normally distributed with a mean of 10 and a standard deviation of 1. Okay? So, while the amount in a type B cell is normally distributed with a mean of 14 and a standard deviation of 2. To determine whether a cell is type A or type B, the amount of chemical is in the cell is measured and the cell is classified as a type A if the amount is less than a certain amount value of chemical C, and as a type B Otherwise, my goodness, I told you it was a mega doozy, didn't I? Goodness. I think we need to read this again, guys. Now, we've got a certain amount of chemical type in a type A cell is normally distributed with a mean of 10, standard deviation of 1. Yeah, got that. And while the amount of the same chemical in a type B cell is normally distributed with a mean of 14, that's higher, and a standard deviation of 2, so it's also wider. So we're trying to determine, given a random cell, if it's a type A or a type B, I think, and the amount of chemical is the determinant of this. So if we measure the amount of chemical and we get it to be a certain, less than a certain specified amount C, value C, we call it an A, and if it's more than that, or equal to that, I suppose, we call it a B. I get it. Do you get it? Alright, I think I've got the gist of it. Now, let's look at part A. If C is 12, calculate the probability that a type A cell will be misclassified as a B, that means it's really an A and we're calling it a B, and the probability that type B cell will be misclassified as an A. Goodness gracious me, we need a picture. We desperately need a picture. Come on, let's draw a picture. Alright, there's my A. There's my A, okay? Yep, right? Do you get that? See, I'm saying that tail above the 12, the value of C is 12 in this part A. That right-hand tail above 12 would be classified as a B, but it's still really an A. You get that? Alright, good. That's why you need a picture, guys. Look, how could you ever work out all that gobbledygook without a picture? So draw a picture and do yourself a favour. So this is this right-hand graph is the B cell. So presumably if we've got less than 12 in that left-hand tail, then we're calling that an A, but it's really a B. So there, those two shaded in tails, the right-hand tail on the left-hand graph and the left-hand tail on the right-hand graph, are the probabilities we're looking for, because they're the misclassification probabilities, yeah? Now I think we can do this, don't you? I think it's easy. Easy now we've got it interpreted. It's easy to do. So, okay, for A, misclassified as B, we're just going to look at the probability that the probability for 12 and above, aren't we? Yes, that's right. So we want the probability, which is a normal CDF, isn't it? Of course it is. So let's go for it. So the lower bound is 12. The upper bound is what? Come on. Infinity. Okay, to infinity and beyond. So we're also going to plug in mu as 10 and sigma as 1. And what are we going to get? The probability comes out is 0.0228 to 4 decimal places, and that's the one we want. Okay, and that's the correct answer because I looked it up. All right. Now let's do the same thing for B. It's easy now. Yeah, that's B misclassified as A. All right. Now that's the left-hand tail. So we can look up. This time we're going to also look up a normal CDF as well, and we'll allow you work it out. What's the lower bound? What's the upper bound? Come on. Yeah, lower bound's minus infinity, and the upper bound is 12. Yes, and we do it on our calculator. Mu's 14, sigma's 2. What do we get? I'm running out of room. 0.1587 to 4 decimal places, Mr. Box. Now that's it, and that's the correct answer as well. So there you go, guys. That's part A. Now part B, if you thought that was hard, you ain't seen nothing yet. Now, part B says find the value of C for which the two probabilities of misclassification are equal. Well, so there's a certain value of C which isn't 12 because they weren't equal in the previous part A. There must be a value of C for which the probability of the right-hand tail of the A situation is the same as the probability of the left-hand tail of the B situation. Do you know, I smell a Z here. We're comparing two distributions. We need to compare them with each other, guys. Yes, I think so. We need to compare two different distributions, yes, for variables which have the same probabilities, which is a case for Mr. Z. Mr. Z strikes again when you least expect. So let's go for it, Mr. Z. We love you. You save us. Yeah, now there's my A, there's my B, rewritten as standard normals, everybody. Now look, this is falling into place very nicely. For both of them, mu is 0, sigma is 1, okay? Because they're both standard normals now. So all I've got to do, ladies and gentlemen, is work out what that ZA and that ZB are, which, incidentally, will be the same number, because it's the same probability, except, ladies and gentlemen, that 1 is a plus and 1 is a minus. Isn't that right? How gripping is this? It is gripping. Probabilities are equal. Yes, they are. Okay, so I'm saying to you, ZA is equal to minus ZB. Okay, do you see? Yippee, we see all right. So therefore, what we're saying is that C, our value that we've got to get, minus mu A over sigma A, is equal to minus C minus mu B over sigma B. Okay? That's what I'm saying, the variables. I'm saying that ZA is minus ZB. Okay, that's what it translates to. Now we can fill in all the numbers except Mr. C, and he's ours for the taking. Here it comes, here it comes. The grand finale approacheth. Right, so let's just simplify that a bit. And what do we get? We get that. Okay, just get all the C's over one side, all the numbers over the other side to get that. And C is 34 over 3, which happens to be 11 1/3. Whoopee-doo. There it is, okay? So there's your answer. See what a beautiful thing it is when Mr. Z comes to the rescue. He is truly a great warrior for our cause. And what have you got to say for yourself, Mr. Light Globe? Normal is cool. It's very cool. Absolutely cool. Yes, so thank you for that, Mr. Lightbulb. And thank you for watching. That's the end of our little show for today. Okay? Now you go off and do plenty of practice, okay? And get really good at this. And we'll see you anon. Okay, bye.